Hello everyone, welcome to my channel. Today I am going to talk about cell momentum balance. Here I will discuss velocity profile development for laminar pipe flow. So here is the problem statement and setup. The objective of this problem is to develop velocity profile for steady laminar flow in horizontal circular pipe. So here I am choosing R and X coordinate system. Here are the given statement. So the pipe is horizontal, the horizontal circular pipe of radius r, steady incompressible flow, Newtonian fluid with viscosity mu, pressure driven flow with pressure drop del P. Here I have to find the velocity profile Vx of r using cell momentum balance. Now here are the key assumptions. So first is steady flow. So dou Vx by dou T is 0. Incompressible fluid means rho constant. Fully developed flow, that means Vx is function of r only. So there is a no velocity variance in x direction. The velocity is varying only r direction. So that is Vx is equal to Vx of r. Newtonian fluid, so Newton law of viscosity we can apply. So tau Rx is equal to mu dVx by dr. No slip boundary condition at r is equal to capital R, velocity is 0, means at well here the velocity Vx is equal to 0. Now here Vx is max at center line, and we are considering this is a horizontal pipe, so no gravitational effect in the flow direction. Now here is the cell element, so we are taking this cell that radius delta r. So in that horizontal pipe, the geometry inner radius r, outer radius r plus delta r. So here that is r plus delta r, that is delta r, and pipe length is L and pipe radius is capital R. Now here momentum balance framework. So general momentum balance. So rate of momentum accumulation is equal to rate of momentum in minus rate of momentum out plus sum of forces. So for steady flow, so rate of momentum accumulation is 0. So for fully developed flow, net momentum transfer is equal to 0. That result, summation of all forces on the cell is equal to 0. Now here that forces acting on the cell. So here tau is acting on the surface as well as inner surface and outer surface. So one is pressure force. So pressure force acting upstream phase like Px into area. Then downstream force. So here this is the downstream. So Px plus del x into area. Now viscous shear force. So that is acting on the inner surface here inside that. So tau Rx into area, outer surface tau Rx r plus delta r in plus into area. So that is the outer surface force, and body force that is negligible for horizontal pipe. So no gravitational force is acting on that horizontal pipe. Now pressure force, so Fp in, so that is P of x into 2 pi r delta r. P out, that is minus, because if you see here that sign means this is upstream direction and that should be downstream direction, but force is acting perpendicular to the surface, so that is negative. So that is minus P of x plus del x 2 pi r del r. So Fp net, so that will be del P. Del P means Px minus Px plus del x. So del P 2 pi r dr. Viscous force, so F tau inner, so tau Rx r into 2 pi rl, and Ft outer, so minus tau Rx r plus del r. So here 2 pi r plus delta r into L. Now complete force balance, so del P 2 pi r del r plus tau Rx 2 pi rl minus tau Rx r plus delta r 2 pi r plus del r into L is equal to 0. Now here the del p is equal to p of x minus px plus del x. Now from here, so uh, we already that did the balance. So now we are divided 2 pi lr, so that will be, so it will be del p by l into r, tau rx r into r minus tau rx r plus del r plus del r by del r. So if we do the rearrange, so tau rx r plus del r into r plus del r minus r tau rx r into r del p by l r. So if I take that limit del r tends to 0, so we'll get d by dr r tau rx is equal to del pl into r. Now from the differential equation we got that. Now integrate from r is equal 0 to r, so 0 to r d dr of r tau rx dr is equal to 0 to r del p by l r dr. So left hand side, so that will be r of tau rx minus 0. Right hand side del p by l 0 to r dr. So that will be del p r square by 2l. So finally we'll get tau rx is equal to del p r 2l. Now according to Newton's law of viscosity, tau rx is equal to minus mu dvx by dr. Now substitute shear stress profile, so minus mu dvx dr is equal to delta pr by 2l. So solve velocity gradient, so dvx by dr is equal to minus del pr 2 mu l. So what is the physical meaning? Velocity decrease from center to wall, so negative gradient proportional to the radial distance, and steeper gradient for higher del p or lower mu. Now from velocity gradient, if we integrate, so that will give vx is equal to minus del p 2 mu l integrate of r dr. So now again if I do the integration, so we will get minus del p by 2 mu l r square by 2 plus c1. So c1 is the constant. So vx of r is equal to minus del p r square by 4 mu l in plus c1. So we have to find out c1 using boundary condition. So vx r is equal to 0. So means at wall no slip boundary condition. So vx r is equal to 0. So if we plug that, so c1 will be del p r square 4 mu l. So now we again plug that value. So vxr will be del p by 4 mu l r square minus r square, small r square. So standard form vxr is equal to del p r capital R square by 4 mu l 1 minus small r by capital R whole square, but that will be the velocity profile. So that is nothing but Hagen-Poiseuille velocity profile. So Vx are nothing but del p r square 4 mu l 1 minus r square by capital R square. So now what will be the characteristic of the profile? Parabolic distribution, maximum velocity at center line r is equal to 0 and 0 velocity at wall r is equal to capital R, and axisymmetric about center line. So now here maximum velocity r is equal to 0. So if I plug r is equal to 0 in this profile, so we'll get this on. So here that is del p r square 4 mu l. Now average velocity v average, so 1 by pi r square 0 to r vxr 2 pi r dr. If after plugging that vxr value, then if we do the integration, so we'll get del p r square by 8 mu l. So that is nothing but vx minus 2. So that is v average. Volumetric flow rate, so q is equal to pi r square v average means area into velocity. So that will be pi del p r to the power 4 by 8 mu l. So wall shear stress, so that we can easily calculate by tau r x is equal to minus mu dvx by dr. Using that we'll get the del p capital R by 2l. Now summary of the key results: shear stress tau rx del p r by 2l, velocity profile vxr del p r square 4 mu l 1 minus r by r whole square or r square by capital R square, maximum velocity vmax del p r square 4 mu l, average velocity v average del p r square 8 mu l, flow rate Q is equal to pi del P R to the power 4 8 mu L, and wall shear stress tau W, that is del P capital R 2L by 2L. That's it. Thank you.